Most of us just think of spiders as simple bugs dwelling in the dark corners of our homes, but they belong to an entirely divergent evolutionary branch. They operate on internal mechanisms that directly defy standard animal biology. To observe these biological anomalies in the wild, we are going to look closely at the Golden Orb Weaver. Understanding how this creature survives requires discarding everything you know about normal vertebrate or insect biology. Watch the orb weaver move across this wide gap in the forest canopy. Its locomotion relies on fluid dynamics rather than traditional muscle mechanics. Humans and insects use opposed muscle pairs to move. A flexor muscle bends the joint, and an extensor muscle pushes it outward. The spider leg lacks extensor muscles entirely. To open its legs, the spider uses its heartbeat. It pumps hemolymph, the arthropod equivalent of blood, directly into the leg cavity, forcing the joints open through sheer hydraulic pressure. This bar chart illustrates the quantifiable pressure generated by the system. When preparing to jump, a spider creates an internal hydraulic pressure spike that rivals a standard industrial mechanical piston. This explains a morbid consequence of spider anatomy. When a spider dies and its heart stops pumping fluid, the internal pressure drops. Only the flexor muscles remain engaged, pulling the legs tightly inward. The spider navigates the world using a series of pressurized fluid events rather than the muscle-driven leverage found in mammals. High in the canopy, the orb weaver begins constructing its massive web. Spider silk is not passively squeezed out of the body like toothpaste from a tube. The spider physically pulls it, and that mechanical tension is required to synthesize the material. Inside the spinneret gland, the protein sits as a chaotic liquid. As the spider applies tension to the thread, the liquid molecules instantly snap into alignment, crystallizing into a solid lattice structure. This line graph maps the elasticity and tensile strength of the resulting thread. This newly formed biological silk yields a higher tensile strength than structural steel and absorbs more kinetic energy than Kevlar before snapping. The spider actively controls the chemical properties of this silk in real time. It formulates dry, rigid threads for the web's structural frame and alters the composition to create highly elastic, sticky lines for the capture spirals. It creates specialized high-performance polymers on demand, functioning as a real-time chemical manufacturing plant, operating entirely at room temperature. With construction finished, the spider settles into the dead center of the web and stops moving. Despite having 8 eyes, many web-building spiders have surprisingly poor vision. They cannot clearly see their prey approaching. The spider relies on the web itself. The silk threads act as a literal extension of its nervous system, stretching out into the open air. The spider reads specific vibrational frequencies, traveling up its legs to identify disturbances. A slow, rhythmic wave signals a gust of wind, while a chaotic, high-frequency wave identifies a struggling fly. To find its target, the spider plucks the silk thread like a guitar string. It reads returning vibrations to echolocate the trapped insect. The spider's sensory awareness extends far beyond its physical body. Its consciousness actively encompasses the entire geometric structure of the web. The impact of this specialized anatomy extends far beyond the individual web, reaching the macro scale of the entire global ecosystem. Each spider leverages its hydraulic speed and crystalline silk to consume hundreds of times its own body weight in prey annually. When scaled to the global population, this predation is the primary barrier preventing insect biomass from overwhelming terrestrial vegetation and collapsing agricultural systems. Hydraulic joints and vibrating sensory webs aren't biological novelties. They are specific mechanical answers to the problem of survival that have been operational since before the first dinosaurs appeared. While most terrestrial designs have been discarded or overhauled by evolution, the spider's blueprint remains largely unchanged after 380 million years.